Welcome. Today, we're going to pull back the curtain on the machine learning workflow. This is the core process that powers pretty much everything, from the simple predictions on your phone to the super advanced AI systems you hear about at events like the India AI Summit.
So, how does an AI system actually learn from data? I promise you, it's not magic. It's a structured, repeatable process, and if you're a software engineer, you're already wired to master this. It's all about turning raw information into smart action. Okay, let's map out this journey.
We've broken this down into a little 3-day boot camp. Day 1, we'll learn the rules of the game. Day 2 is all about cleaning up the mess that is real-world data. And on Day 3, we'll actually make a prediction. Then we'll wrap it all up. All right, let's kick off Day 1. This is where we lay the groundwork. Think of this stuff as the absolute non-negotiables. These are the principles that every single successful machine learning project is built on top of.
First things first, you've got a choice to make. What kind of problem are you trying to solve? With supervised learning, you have the answers already in your data, and your goal is to predict a specific thing. But with unsupervised learning, you don't have any answers. You're just asking the machine, hey, find some interesting hidden patterns in here for me.
Now, this next bit is, well, it's probably the most important rule for building a model you can actually trust. You have to split your data. The model learns on the training set. You tweak it using the validation set, but that test set, you lock it away and only touch it once at the very end for a final, honest grade. If you don't do this, it's like giving a student the exam questions to study from. They're just going to memorize the answers.
To make all this real, we're going to be using the famous Iris dataset. You can think of it as the hello world of machine learning. It's simple, it's clean, and it's perfect for letting us focus on the workflow without getting bogged down.
Okay, here's the code that makes it all happen. Now, look closely at the parameters we're using for train_test_split. That little stratify command, that's our insurance policy. It makes sure our training and testing sets get a fair, balanced mix of all 3 flower types. And random state, that is absolutely non-negotiable for any serious project. It makes sure your random split is exactly the same every single time you run the code, which is a lifesaver for debugging. All right, on to Day 2. Now we get to roll up our sleeves and do the, let's call it the less glamorous work. But honestly, this is the most critical part: data cleaning and pre-processing.
You've probably heard this before. Garbage in, garbage out. It is the golden rule of data science. I'm telling you, you could have the most powerful, most expensive model on the planet. It won't save you from messy data. The quality of what you put in completely dictates the quality of what you get out, period.
And this is what real-world data actually looks like. It's never perfect. To show you what I mean, we've intentionally messed up our clean Iris dataset. See those nans? Those are missing values. And that supple length of 12.9? That's a crazy outlier. This is the reality you have to deal with. So what's the plan? How do we fix this mess? It's a simple 3-step attack. First, we're going to fill in or impute those missing values. Second, we'll deal with that crazy outlier. And third, we're going to scale all our features so the model treats them all fairly. Okay, the code here shows a super important pattern that trips up a lot of people when they're starting out. You always fit your cleaning tools, the imputer, the scaler, whatever, only on the training data. You learn the cleaning rules from your training set, and then you apply those exact same rules to transform all of your data sets. This prevents something called data leakage, which is a sneaky bug where information from the future accidentally contaminates your training process. And hey, look at the result. See? All the missing values are gone. That wild outlier has been tamed. And now every feature is on a nice, comparable scale. This is data that's clean, consistent, and ready for a model.
Welcome to Day 3. Now that we have this beautifully clean data, we can start asking different kinds of questions. So we're going to pivot. Instead of trying to put a flower into one of 3 buckets, which is a classification task, we're going to try a regression task. We're going to predict a continuous number, the exact length of a flower's sepal.
To pull this off, we just switch our model to a linear regression model. Now, for this kind of problem, our goal totally changes. It's not about being right or wrong anymore. It's about being as close as possible to the real number. And that means our report card changes too. We go from looking at accuracy to something called R-squared.
So how'd we do? How do we grade this new model? For regression, we're going to look at 2 key things. First, how big are its mistakes? On average, that's mean squared error. And second, how much of the data story can our model actually explain? That's the R-squared score. Let's check the numbers. First up, our mean squared error on the training data.
We're getting about 0.10, which is pretty low. That's a great first sign. It tells us the model was definitely able to learn the patterns from the data we gave it.
Next, the validation error is just a little bit higher at 0.12. And this is exactly what you want to see. This is perfect. It means the model isn't just cheating and memorizing the training data, it's actually generalizing what it learned to new examples it's never seen before.
And now for the final exam, the R-squared score on our untouched test data. We got 0.85. That's a really solid result. It basically means our simple little model can explain about 85% of the variation in sepal length just by looking at the other features. That's not bad at all.
And because we use the simple model like linear regression, we can actually peek under the hood and see what it learned. These coefficients tell us how much each feature influences the final prediction, and it looks like the model decided that petal length has a really strong positive relationship with sepal length. Pretty cool, right?
So, we've made it through our 3-day bootcamp. Now let's just take a step back and look at how all these pieces fit together into the complete end-to-end workflow. And here it is. The whole thing is a loop, a cycle. You define your problem, you prep your data, you train a model, and you evaluate it. But you almost never stop there. Based on how well it did, you go back, you tweak things, and you repeat the cycle, making it better and better before you finally deploy it.
Okay, let's just boil this all down. What do you really need to remember? First, know your problem type. Second, always use a train validation test split. Third, cleaning your data is not optional. It's like 80% of the job. Fourth, remember the golden rule. Fit only on the train set to avoid data leakage. And finally, pick the right way to measure success. Master these 5 things, and you're ready to tackle almost any ML project.
So there you have it. We've just walked through the fundamental blueprint for turning raw data into real decisions. The only question left is, what problems are you going to solve with it? What will you build first?